everyone. Today I'm speaking with Sheetanshu Tyagi, co-founder at Bangalore-based lithium-ion battery technology startup EMO Energy. Hi, Sheetanshu. Welcome to EV Reporter podcast. So, Sheetanshu, to start with, can you explain what is unique about EMO Energy's battery packs?
Sure. So before I go into the question a little bit, to give you a little context on how we got what we're doing, right? So Rahul and I have been in the industry for a while, trying to design battery packs for different companies. We realized that specifically for the 2 and 3-wheeler space where we started and that's where we operate, a lot of battery packs today have a very specific kind of architecture, a very specific kind of design, which then yields certain amount of performance and safety. So there's a lot of cylindrical cells or prismatic cells placed in a cell holder orientation, mostly spot welded with nickel on both sides. And then there's an arrangement of some sort to hold that together in a module of sorts, and then do basic BMS connections. And there's been a lot of advancement some companies have done to improve this architecture. So they used different potting compounds, they used thermal foams, there's phase change materials. All of these now help in a certain amount of safety and then cooling, which then become the two big objectives to really be solving for lithium-ion battery packs. And around that, we've seen a lot of architectures which now have used phase change to deploy a certain amount of thermal safety and then a certain amount of cooling, let's say at 40 degrees. So there's a certain amount of energy absorbed, which you can then retain and then still do power at 40, 45 degrees Celsius in hotter climates. But that we felt was the limit. So there's cars, there's trucks, there's buses, they use water-based cooling, they have cooling channels, different arrangements, serpentine, flat, bottom, top, different arrangements. But even there, we saw that there's a limitation in terms of how conduction is happening, how heat transfer happens. You have indirect contact, you have multiple interfaces. And in the end, the effective thermal conductivity that you're actually getting for cooling, and then the entire amount of material, the amount of cost you've spent on the safety material itself, is pretty large to when you consider a system for a 2 and 3-wheeler, which not only has to be affordable, but also has to be light, portable, and there's so many requirements to this segment that has to withstand abuse. So we felt like there had to be a new approach for where we designed the architecture of a battery pack from scratch. And there were 3 or 4 things that became unique to us. So cells, using cylindrical cells, orienting them in opposite ways so that if thermal runaway happens, they actually oppose each other and have different venting parts, having very advanced vents for portable packs or even for 2-wheeler packs. And then one of the bigger things we did was to use a fluid-based kind of cooling and safety system. So a lot of people call it immersion cooling. There's different names around it. Essentially developed a fluid and a control system around it, which then allows fluid to keep circulating within the pack in a very specific manner. Because the system is now solving for thermal cooling, heating, and also a safety system. Because that compromise has to be very clear, because you have thermal conductivity, which helps in cooling, but you have the heat capacity and the amount of energy absorption in the safety part of it. So to balance both, we felt that instead of using cooling channels plus foams, we use one kind of combined system, which then becomes a compromise of both in some ways, but a much better solution for the applications we're going after to then give better power, better safety, and then overall better life cycles.
Okay, correct. So what is your market presence right now or market readiness right now? Can you talk about that?
Absolutely. So we think of ourselves in 3 tiers as, let's say, products or companies. There's a base level product pack, which has been for 2 and 3-wheelers. It's a portable battery pack. That is in mass production right now. So we have hundreds of them on road. We're doing a lot of pilot testing and refining some of the, let's say, software bugs, some of the thermal analysis part to actually real test on road. That is actually now to a point where we have validation around the safety, the thermal performance, and the life cycle part of it. So we've been kind of aggressively pushing that out amongst a lot of fleet operators, OEMs, and kind of finalizing some partnerships around that whole aspect. But there's also a lot of work happening on the larger systems, which then we call Zen Rig, which then becomes for tractors, for light mobility, sectors that haven't been, let's say, researched upon as much as maybe passenger cars or even buses for that matter. But there's a lot of tractors, mining, construction, 3-wheelers, LCVs. These are relatively newer forms of electrification, a lot of them using even low voltage systems, which again, I feel like India is very good at. Maybe high voltage systems, only some of us have done really well. But yeah, there's a lot of work to do on those fronts. And then using those modules, using that technology, keeping them modular in the way we construct our modules to then use in energy storage. Those are all pilots today. We have battery packs up to 60 kilowatt hour, which we're testing with a few companies. But I'd say those go into production sometime next year.
Okay. So with respect to the packs that are already on the road in testing, so and you have certain claims of advanced life cycle, better safety, and so on. So what kind of external validation have you received so far from people who are using your products?
Yeah, absolutely. So there's, again, I'll break this down in safety, performance, and then life.
Okay.
So from a safety perspective, we've done, I'd say, at least 25 tests for thermal propagation, different cells, different orientations, different forms of testing. So overheating, which is an ARI mandate, we've done very aggressively for multiple cells. We've also done nail penetration because we feel like there's a much more aggressive input to the cell once you do that kind of a test. So from a safety perspective, we've tried to use every single standard in the world to be able to actually propagate cells in whatever manner possible, to then see if there is no propagation from one to another. And we've essentially been advancing, let's say, the fluid we use, the amount of pumping we use, what kind of controls we use to monitor and then predict that it's happening. All of that has been improving quite consistently, but we have a base level where we're testing that for any kind of cell possible, and it works. Like there is no more than 10-15 seconds of venting of smoke. There's no visible fire or no explosion as such. So from a safety perspective, there's a phase 2 mandated for multiple versions of our battery pack. From a performance part, we've been testing with vehicles for almost a year now, for even over a year. There's enough life cycle data where we've already established over 500 cycles on road for multiple vehicles. So we're seeing a very, very good correlation between our road data and then the lab data, which we've tested for multiple cells and packs, all the way up to 2000 cycles. And we're essentially seeing around 1% degradation every 100 cycles. So that's a good metric for us. And that then puts us around 20% degradation for 2000 cycles. But the interesting thing is this we're doing for NCA cells. So standard BAK version cells that are in the market, no special cells. We use NCA chemistries because, again, it's just a little bit better in power and I feel overall reliability. But yeah, we've essentially been able to manage thermal propagation for that, be able to prove out road data with a combination of our thermal system, our algorithms that we're using for life extension, and then our BMS platform too.
Right. And very interestingly, you mentioned the chemistry you're using, NCA cells. So can you tell us more about your choice of the chemistry and also form factors, of course?
Yeah. So from a chemistry perspective, I feel like we are genuinely truly agnostic. And in the sense that we choose it like a menu book. So two-wheelers, I feel like, need portable packs. There's a certain amount of weight that matters. There's a certain amount of volume that matters. To us, it was very critical to get the smallest form factor possible, such that you can literally put this in any vehicle. Maybe except for, let's say, an Ola or Ather, you should be able to, let's say, put in the boot of every vehicle, which is a standard for, let's say, fleet vehicles at least. So NCA became an obvious choice because we did test LFP. We have a pack that we're building even for two-wheelers with that. But it is a certain amount of compromise in weight, volume that you see. There's obviously a lot of work happening to improve that watt-hour per kg number for LFP, but it's not there yet. So there's a lot of work we specifically do with NCA chemistries. We work with the best in the world from China and Korea to see the amount of advancement happening there. We feel like portable packs, especially the kind that produce a good amount of power, there is a lot of life cycle you can get even from NCA chemistries. There is an obvious cost difference. It is costlier than LFP. But yeah, just for this specific application, it really doesn't get much better. And that's why you see some of the bigger two-wheeler companies also sticking to maybe NMC or NCA, because there is a vehicle advantage you get as a whole. But that being said, again, we use LFP for our larger packs. Three-wheelers, four-wheelers, we use LFP very very exclusively, in fact, because there the weight and volume, the TCO, the cost actually makes sense. Like LFP is under $100 per kilowatt hour now. So it's really hard to then justify the $120, $130 per kilowatt hour for an NCA cell. And we are also now even testing sodium ion for that matter. There's 7 or 8 companies in China we're working with to see what advancements happening. And there are a lot of cells now that can actually guarantee you that charge discharge curve. But I feel like the life cycle and the overall reliability of that particular chemistry is still early. So hopefully by next year, we'll be implementing that in packs too. To your other question on the form factor, we actually exclusively have been using cylindrical cells so far. And we're not really attached to it. We are doing projects with prismatic too, but cylindrical cells, I feel, offer two huge advantages, especially for a country like India. One, the availability and the kind of changeability of suppliers. Like you can have 5 suppliers supplying you the exact same cell, the exact same dimension, and know that if I ran out of one country, you can literally switch countries, switch companies overnight and not lose that specification and not have to redo your contracts, etc. And the other part to it is that the form factor also genuinely allows for a lot of what we call the agnostic part of this, right? So in the same form factor, in the 32-140, for example, which we use for LFP, we can also just put sodium ion tomorrow. There's a small reduction in chemistry, but all our tooling, all our capex, everything just carries forward. We can transform that literally overnight into a different kind of cell, and you never even know. The customer would actually obviously experience a difference, but yeah, as a whole, cylindrical just offers that modularity and scalability, which I feel the Indian companies will really need, because prismatic LFP, for example, is the most in-demand cell in the world. Like companies like Goshen and CATL are selling out to the US and EU. So for us to expect to get that level of cell is hard. But today we could get maybe like an LG, Samsung, and I'm just naming companies, but we could get that level of cylindrical cell. So yeah, that's why we stick to cylindrical cells at least today.
Okay. And if you talk about, again, going back to the two-wheeler packs that are already in testing, how would that compare with the more prevalent battery packs in the market in terms of cost?
So from a cost perspective, we're actually very competitive. I'd say, just to put out a number, there's a certain market standard that's maybe around 18,000 per kilowatt hour. Let's assume that for the two-wheelers, and maybe three-wheelers is a little lesser, 15,000 or so per kilowatt hour. We're right about there. Like based on volume, based on scalability, we could essentially go back and forth. But the important part for us is that every single component except the cell is developed from scratch, all the way from the cell holder material to how we develop the connections to the bus bars to the containers. Everything is from scratch, and that's really allowed us to optimize cost at scale. So even the plastic parts we make, all of them are built in the same factory where the assembly happens. We have very tight control on every single process, and we use, again, very standard chemistries where you could buy cells at less than $2 a cell. So the ability to then gain the life cycle advantage we gain from these cells and then offer the TCO we offer not only allows us a premium, but then also allows us market standard pricing. And that is essentially one of the biggest things we focused on. How do you offer fast charge? How do you offer this life cycle advantage without disrupting that upfront cost, without going to somebody and saying that, no, you have to now wait for 2 more years, you have to wait for that. So we've been trying to be very competitive there. And yeah, we're at scale, we're essentially at those numbers.
Okay. And in terms of your current production setup, tell us more about it. Where is your setup and what is the current scale?
Yeah, so we have a factory actually 2 hours from Bangalore and Mysore. We have essentially an entire assembly line set up there with a plastic injection molding, with the casting, all kind of in the same, let's say, campus, essentially. The automation for a lot of the key processes we have in place, so the cell sorting, we'd use a lot of key processes like how we apply glue to the cell holders, bus bar gluing, wire bonding, UV curing, kind of pack testing. All of that is automated. We're essentially doing almost 25-30 packs a day already, and we'll be up to a lot more essentially in the next couple of months. And yeah, we're essentially supplying to multiple fleet operators out of that facility. And this is a full, properly tooled mass production pack. This uses nothing prototype. Every component is actually at the point where we've got the final production tooling ready for all of these now.
Right. Okay. So in terms of OEM qualification, can you tell us what kind of OEMs are you currently consulting with, working with, and what kind of, when can we actually see your packs pre-fitted in the vehicles that come on the road?
Right. So there's a lot of partnerships we're working on, and without naming too many, there's anyone in the, like, say, there's a bunch of companies in the top 10, there's a bunch of companies in the long tail, as you call it, that we're working with to do almost 100 or so packs a month now. There's a lot of, I'd say, yeah, testing and a lot of road validation we'll be seeing in the next couple of months, because the last 3 months is when we've been scaling up a production facility, supplying pilots, then pre-production, and then final production packs. So we are actually going to be showing a lot of the data that we'll talk about at least in the next 2 or 3 months. Yeah, with some of the companies that you hear. Yeah, some of the big names. Yeah.
Okay. Now, if we go into the technical part of how your battery packs work, so can you explain what is that thermal management process, the proprietary thermal management process that you have developed? And after that, we'll also come to the pack construction. What are your innovations there? What is it that basically translates into better performance and better safety?
Yeah, absolutely. So from the thermal management perspective, there's the fluid, there's the electronics, the sensors, and I'd say the control system around it. And then there's what I call the pumping and heating system. So all three of these work in conjunction to essentially establish the thermal management system. So we submerge the entire battery pack in fluid. We have multiple pumps and multiple heaters, kind of and heat rejection devices at the bottom of the pack, which are forcing fluid through the center of the pack in a very specific direction. So all of the cells are then seeing the exact same amount of flow, the exact same amount of pressure across the entire cross-section. The fluid is then being rejected to the outside around the aluminum surface itself into channels. And this then rejects the heat to the atmosphere through like an aluminum heat sink to the air, and then forms a very, I'd say, straight and clean path of conduction from cells to the fluid to the housing and then to air. So within the pack, we can essentially always maintain within 1 degree Celsius, even when we're doing high rate discharge or high rate charge. And if you have enough airflow around the pack, if there's enough heat rejection from the housing to the atmosphere itself, which is the easy part here, then there is enough heat rise you can maintain even when you're essentially doing heat rejection at 45 degrees Celsius. So for us, the objective always was to maintain the best possible path between the cell to the housing. And how do you keep making that heat rejection as clean as possible? So the fluid we use is a thermal conductivity around 0.2 to 0.3 watt per meter Kelvin, very high specific heat capacity, so it can absorb a lot more. Not as much as water, but it's a mineral oil based kind of compound. So it does absorb, let's say, maybe 30% of what water does. But the fact that you don't have to go through two interfaces to then get to the fluid is a huge advantage. So from a thermal management system, that becomes key. There's multiple sensors across the entire pack. We actually have a sheet in the middle, which is measuring temperature across every cell. So it's not really an NTC per se, but it's a thermal chamber, a vapor chamber essentially, where if there's a certain amount of pressure acting on any of the cells, it knows that at least one cell is, let's say, going above 60 degrees, and it'll cut off the entire pack and put the fans in kind of overflow mode. So they'll be at 12 to 16 liters per minute, really rejecting fluid as fast as possible. So the cell doesn't really, for us, that easily even go to 300 degrees. Like when we're doing the test, it's very hard to do. But one thing we've seen is that if you hold the fluid static, if you can use the best fluid in the world, you can use the most amazing kind of coolant in the world. But if you're holding it static, if you're not controlling it, if the monitoring system doesn't know when to reject it, it's quite difficult to get it right. So a lot of our work has gone into that entire architecture around that control system and the flow-based system that I spoke about. And complementing that is also the architecture of the pack. So the module inside we hold with cell holders, and the pack on the outside is fully aluminum. But between those two, we kind of have rubber dampers. There's actually 8 kind of suspension rubber points, which then form this kind of eggshell construction, which we like to call it. And if there's impact on the outside, then it's actually taking this impact and not allowing, let's say, cells or the wire bonds to really see that vibration, mechanical shock, or impact. So that's been one of the key understandings, because a lot of the portable packs go through a lot of drop and abuse, and they're usually held in kind of a press fit environment. So you tape the cells or you hold these packs together and just press fit them into a pack. And there's maybe thermal pads and pushing them against the housing. But this arrangement is kind of making it shock-proof in a way, but all of the load is then going to your cells. So that becomes quite hard, and we've essentially tried to move away from that form of construction. And we have IoT kind of the GPS on the top. We have a display on the top. We have 2 vents kind of diagonally opposite, pressure activated at a very specific point, done a lot of testing to actually develop our own kind of metal vents for that. And all of these kind of features then go into the mechanical part of it. And even on the BMS, there's a lot of innovations we had to do in terms of what kind of cell balancing we're doing. So we do really fast passive balancing, upwards of 2 amps, and we use only 2 MOSFETs. So our MOSFETs are incredibly cool. Our balancing is incredibly cooled down because the fluid is also flowing on the whole BMS. So now we've been able to redesign our BMS architecture because of the way we're actually constructing our pack. And a lot of the work has gone into understanding how do you measure high current and reliability so as to then do faster balancing, to do just a lot better temperature control, so you have better cutoffs. Because a lot of the packs that, let's say, go into propagation or have had issues, have a lot of cell level quality issues, but even big temperature gradients, right? Like, so your lowest cell could be at 55, 60, but highest could be at 70, because you aren't really monitoring the entire pack. You might have 3 or 4 NTCs differently placed. So all of these problems we've really kind of tried to address through our entire battery pack design.
Okay, wonderful. So otherwise, I think immersion cooling is not very popular in two-wheeler packs. Is that correct?
Yeah, absolutely. I'd say there's multiple companies now trying to see how to actually implement it, because I feel like it is a very strong, I wouldn't say it's the best solution, but it's a very strong compromise between all of the points that you have to get right. Like, if you do, let's say, thermal potting compounds, or you do foam, or you do PCM, or you do water-based cooling, or some different forms of liquid cooling, they all have their own advantages and disadvantages, right? But I think at the end of the day, for a very specific application, for us, for example, it's fleet two-wheelers. It's the 8 million two-wheelers that do hyperlocal delivery, right? That's the first segment we want to solve. For that particular segment, there's a few things we saw had to be kind of ticked off. So the pack has to last like 3,000 cycles or 2,000 cycles or whatever, 5 years, for example. That has to fast charge, but it should be portable, but it should be lightweight, but it should be small. It should just be extremely rugged. It should also have like a good presence. It shouldn't like just be, something that's cheap or low quality. And then it has to work at 45 degrees, but also at 0 degrees. Yeah, there's just so many requirements. So this immersion cooling solves for almost all of them, right? Like, it checks all the boxes. Our pack is actually quite lightweight when you put it in a perspective of the competitors. A 2 kilowatt hour pack is 13.5 kgs. And that's with everything. Like, everything is shoved into it. We have like a large 12 volt DC also, which can power multiple things on the outside. And yeah, the idea is that this can then become the standard for a lot of these, the energy market for the hyperlocal delivery segment. So yeah, we feel like a lot of companies are going to be doing that more and more as we go ahead now.
You are like innovating in the battery tech space, and nowadays there is a lot of talk about standardization for battery swapping. So I just, as an innovator, I want to have your opinion on if a battery standardization for swapping use case will limit people like you from doing your things. What are your thoughts around it?
What I'd like to actually see standardized, and it'd be really nice, is maybe the connector and potentially the form factor. And maybe, so there's 3 things that have to get standardized, right? The connector, the form factor, and your connector communication protocol. There's really not that much more we need to standardize here. And there's nothing really wrong in standardizing those 3. Like, even today for us, in a way, we're using a standard Chagori connector. We're using a standard kind of cubish form factor. And the communication protocol is a derivative of an already existing Chinese kind of CAN matrix. Those are already standards in the market today. Like, without anybody trying to really push these things into the market, they already have become standard. I'd say 90% of the 2 and 3 wheelers, at least in this segment, the fleet segment, are already using similar systems. So tomorrow, if the government came and, let's say, standardize these 3, I would say it's extremely incorrect to standardize a specific company or a specific very derivative of a specific company, but 3 or 4 basic guidelines to where then the industry sticks to those. Yeah, we'd be more than happy to just work with those. Because today, even for us, when there's so many manufacturers in the vehicle side, there's so many companies in the fleet side, linking all of those is difficult. If there was one standard, our internal technology could then stand out and then give better performance, better safety, better life cycle, to then command a specific place in the system. But yeah, more than happy to work through at least those 3 standard protocols.
Yeah, as long as it doesn't define what you do internally, what you put inside. Okay, so as long as that is not mandated by any regulation, you are fine with the form factor and the connector.
Yeah, absolutely. I'd say there is obviously a restriction that's put here, and I understand the issue, because there's a lot of companies that might not meet even one of these. Let's say, for example, form factor. Based on the chemistry you choose, based on the form factor of cells you chose, based on the construction of a pack, that might not meet these standards. Even for us, maybe somebody takes a thinner pack and makes that standard. But yeah, for us, if that happens, we will design to that standard. That's something I'm more than happy to kind of restrict our whole product growth to. But there is the fear that somebody might standardize a chemistry, for example, or somebody might standardize a form factor, for example. And those might be very incorrect things to standardize because there is a lot of continuous development on those. For example, even 21700 is now becoming 4680. LFP might become LMFP or anything, right? You don't even know yet. So those things, it will be very incorrect to standardize. But maybe placing a couple of constraints such that, okay, anybody who wants to set up a swap station, these are your guidelines for the box, these are your guidelines for communication. Do whatever you want inside. You can cool it with an AC, you can cool it with fans, you can cool it with a refrigerant. It's up to you. But yeah, performance, safety, and life cycles, which then again become the key ingredients to really push adoption, are then still maintained by the company, and there's still market competition between those factors.
All right. So thank you so much, Sheetanshu, for taking the time and also sharing all about your technology and your work. I wish you the very best.
Thank you, Prashi. It was great talking to you.